All right, in our talk of kinetic energy and work energy principle, the one thing I'm going to touch on a couple things that might come up in homework, and maybe things you might see on an AP. It's just a couple quick examples that I want to go through. First, we have a car that has an initial and final velocity that's going to speed up, and we want to know how much net work is required to accelerate a 1,000-kilogram car from 20 meters per second to 30 meters per second. This is really straightforward. We know net work is equal to change in kinetic energy. So we know that if we find the change in kinetic energy, we can find the net work. We just got to know final velocity is here. Final velocity is here, and initial velocity is here. So to find my final kinetic energy, I take 1/2 mass velocity squared minus 1/2 mass velocity squared. And I just punch those numbers in, and when I do, I get my work to be 250,000 joules. Pretty straightforward problem. If you see one like this, that's really good shape. Just understand that you got to keep track of initial and final velocities. Don't get them mixed up. If you do, obviously you'll get an answer that'll be different because you're subtracting those numbers. Here's an example that I want to show you that you might think initially might be impossible to do, but then after you do it, and think of it this way, it becomes really easy, and this is thinking about the equations. So we got a car that's traveling this fast. And when it brakes, to get to a final velocity of 0, it goes this distance. So the question is, what if the car is going twice the speed? How far will it go while braking? Okay? And what we want to assume is that the braking force is the same. Okay? So how fast you're going, if you're going faster, does that mean you apply more force? We got to think the work's going to be the same. So we look at the net work, all right? That's equal to force times distance cosine of theta. Since braking goes backwards while the car is moving forwards, our theta is going to be 180, which means work is going to be equal to -1 times force times distance. So our negative force times distance is equal to the change in kinetic energy. Negative force times distance is equal to kinetic energy final minus kinetic energy initial. Our velocity at the end, 0, which means our final kinetic energy is 0. So now negative force times distance is equal to the negative initial kinetic energy. Negative force times distance is equal to -1/2 mv squared. And so the relationship we're looking for is the relationship between distance and velocity. And I'm going to get rid of the negatives so we don't have to deal with those. But distance and velocity squared. That's our relationship. I guess not equal, but it's going to have a direct relationship, right? If we double the velocities, which is what we're doing here. Okay? If we double the velocity. If we double this, since it's squared, distance should increase 4 times. So what that means is, if it's 20 meters at this speed, it'll be 20 times 4 distance at this speed, which will be 80 meters. And that is our correct answer here. So when we look at working kinetic energy theorem, sometimes we can figure this out without having to delve into the numbers a whole lot. We can think about relationships in the equation. And don't be afraid to do that at times because it might make your life a lot easier.